Black holes are among the most fascinating objects in our universe. A black hole is an astronomical object with gravity so strong that nothing, not even light, can escape from it. This artistic representation shows a black hole's incredible gravitational influence on its surroundings. Black holes aren't empty voids. They are actually incredibly dense regions of spacetime. When massive stars collapse, they warp the fabric of spacetime itself, as illustrated by this visualization from the Hubble telescope. A common misconception is that black holes are like cosmic vacuum cleaners, sucking in everything around them. In reality, black holes obey the same laws of gravity as other objects. They only attract objects that come too close to their event horizon. Black holes come in a wide range of sizes, from tiny primordial black holes to stellar mass black holes to the supermassive black holes that sit at the centers of galaxies. What makes black holes truly unique is their combination of extreme properties. They are incredibly dense concentrations of matter with an event horizon, or point of no return. At their center lies what we call a singularity, where our understanding of physics breaks down. Black holes dramatically distort the space-time around them and emit no light of their own, making them invisible, except for their effects on nearby matter. Supermassive black holes are the colossal giants of the universe, dwarfing their stellar counterparts in both size and influence. Supermassive black holes are cosmic behemoths with masses ranging from millions to billions of times that of our Sun. These objects are so immense that they can distort space and time across vast regions. To grasp their immense scale, consider S5-0014+81, one of the largest known supermassive black holes. With a mass approximately 40 billion times that of our Sun, its event horizon would span our entire solar system. These giants aren't wandering nomads. They reside at the centers of most galaxies, including our own Milky Way. At the heart of our galaxy lies Sagittarius A star, a supermassive black hole with a mass of 4.3 million suns, located about 26,000 light-years from Earth. The origins of these cosmic giants remain one of astronomy's greatest mysteries. Several theories exist to explain their formation. They may have formed from the collapse of massive gas clouds in the early universe, from the mergers of smaller black holes over time, or perhaps they are remnants of the first generation of extraordinarily massive stars. Supermassive black holes aren't just passive residents, they're architects that actively shape their host galaxies. As material falls toward a supermassive black hole, it can form powerful jets of energy and particles that extend far beyond the galaxy itself. These jets can regulate star formation by heating and dispersing gas clouds that would otherwise collapse to form stars. Astronomers have discovered a remarkable relationship between supermassive black holes and their host galaxies. The mass of a central black hole strongly correlates with the mass of its galaxy's central bulge. When actively feeding, these black holes create some of the brightest objects in the universe called active galactic nuclei. The powerful feedback from these objects regulates galaxy growth, suggesting that galaxies and their central black holes co-evolve throughout cosmic history. In our journey to understand these cosmic giants, we will next explore what happens at their boundaries, the event horizon, where the laws of physics are pushed to their limits. The event horizon marks the boundary of a black hole, the point of no return. While often referred to as the surface of a black hole, the event horizon is not a physical surface you could touch. Instead, it's a mathematical boundary defined by gravity's overwhelming power. At the event horizon, the gravitational pull becomes so intense that nothing, not even light, can escape. To understand the event horizon, we must first understand the concept of escape velocity. Escape velocity is the minimum speed needed for an object to break free from a gravitational field without additional propulsion. For example, on Earth, the escape velocity is 11.2 kilometers per second. If you throw a ball upwards slower than this speed, it will eventually fall back to Earth. But if it exceeds escape velocity, it can leave Earth's gravitational influence forever. The defining characteristic of an event horizon is that the escape velocity reaches the speed of light. At the event horizon, the escape velocity equals precisely the speed of light, 299,792 kilometers per second. Inside this boundary, the required escape velocity would exceed the speed of light. And since nothing can travel faster than light, according to Einstein's theory of relativity, nothing inside the event horizon can ever escape. Light that originates outside the event horizon can still escape the black hole's gravity. But any light or matter that crosses the event horizon is forever trapped, inevitably pulled toward the center of the black hole. Another way to understand the event horizon is to visualize it as the throat of a funnel-like structure. In this model, the event horizon represents a boundary where space itself becomes so extremely curved that all possible paths lead inward. This visualization helps us understand that the event horizon isn't just a boundary in space, but a boundary in space-time, a point of no return defined by the extreme warping of the fabric of space itself. Scientists continue to study event horizons through observations and theoretical research to better understand the extreme physics at the boundaries of black holes. Through telescopes, theoretical models, and observations, astronomers are piecing together how matter and energy behave at this cosmic point of no return. At the center of every black hole lies what physicists call a singularity, the ultimate point of infinite density and zero volume. Einstein's general relativity predicts that at the singularity, space-time curvature becomes infinite. All matter that falls into a black hole is ultimately crushed to a single point of zero volume and infinite density, where the known laws of physics cease to operate. This diagram shows the structure of a black hole with the singularity at its center. The singularity is not a physical object, but a point where space-time becomes infinitely curved. It has zero volume, yet contains all the mass that has fallen into the black hole. At the singularity, our understanding of physics breaks down completely. Mathematical calculations yield infinities, which physicists interpret as a sign that our current theories are incomplete. The immense gravitational forces and energy densities mean we need a theory that can combine quantum mechanics with gravity. As we approach the singularity, quantum effects likely become important. Some physicists speculate that quantum gravity might prevent true mathematical singularities from forming. At extremely small scales, space-time might dissolve into a quantum foam with unusual properties, possibly even connecting to other universes through wormholes, though this remains highly speculative. The singularity presents profound theoretical challenges for physics. The information paradox asks what happens to information that falls into a black hole. String theory and loop quantum gravity are attempting to develop a framework that could describe singularities without mathematical infinities. Some theorists even question whether true singularities can exist in nature at all. Ultimately, singularities represent the frontier of modern physics, places where our current theories reach their limits, and where the next breakthrough in understanding the universe may emerge. Gravitational lensing is one of the most fascinating phenomena associated with black holes. Black holes have such immense gravity that they actually warp the fabric of space-time around them. This warping creates a curvature in space-time that affects everything nearby, including the path of light. Light normally travels in straight lines, but near a black hole, these paths become curved. This phenomenon is called gravitational lensing. It occurs when light from a distant source is bent around a massive object, like a black hole. When a light source, a massive object like a black hole, and an observer are perfectly aligned, we can observe a perfect circle of light called an Einstein ring. Astronomers routinely observe gravitational lensing around massive objects throughout the universe, not just black holes, but also galaxy clusters. Gravitational lensing is crucial for detecting black holes, which cannot be observed directly since they don't emit light. Their presence is revealed by how they bend light from objects behind them. One of the most valuable aspects of gravitational lensing is that it can act like a cosmic telescope, magnifying distant objects that would otherwise be too faint to observe. Microlensing is a special case where we detect temporary brightness changes when a smaller object, like a stellar mass black hole, passes in front of a distant star. Beyond just detecting black holes, gravitational lensing has become a powerful tool for mapping dark matter and studying the most distant galaxies in the universe. Gravitational lensing provides some of our strongest evidence for the existence and properties of black holes, while allowing us to study the distant universe in unprecedented detail. In October 2024, physicists made a groundbreaking discovery, the first observation of what they called a black hole triple system. This system consists of a central black hole consuming a nearby star while being orbited by a second star at a much greater distance. This discovery challenges our previous assumptions about black hole formation. It suggests that some black holes may form through a gentle direct collapse process, rather than through violent stellar explosions. Traditional black hole formation theory suggests that most black holes form from the violent collapse of massive stars at the end of their lives. However, the triple system discovery suggests that some black holes may form directly from collapsing gas clouds, without the violent supernova explosion previously thought necessary. This gentle formation process would allow nearby stars to remain in stable orbits. In November 2024, researchers uncovered another surprising discovery, a potential link between black holes and dark energy. These studies suggest that the density of dark energy, the mysterious force driving the universe's accelerating expansion, may increase alongside the growth and mass of black holes. If confirmed, this connection could revolutionize our understanding of cosmic evolution and potentially explain the universe's accelerating expansion. It suggests black holes may play an even more fundamental role in the universe than previously thought. Recent years have seen a rapid acceleration in black hole research, with several other groundbreaking discoveries expanding our understanding. In January 2025, scientists observed the real-time formation of plasma jets extending from a black hole, a phenomenon previously only observed over much longer timescales. Recent research indicates that a black hole's spin can reveal information about its formation history, particularly whether it formed through multiple mergers in densely populated star clusters. Scientists have provided the first observational proof of a plunging region around black holes, confirming a key prediction of Einstein's theory of gravity. And a February 2025 study described the creation of regular black holes from gravitational effects alone, without the need for exotic matter, challenging traditional models that include singularities. These recent discoveries are transforming our understanding of black holes and their role in the universe, opening new frontiers in astrophysics and cosmology. The future of black hole research promises profound discoveries with new missions like the Event Horizon Explorer. Building on the Event Horizon Telescope's groundbreaking success in capturing the first image of a black hole in 2019, astronomers are now developing even more powerful tools. The next generation mission, called the Event Horizon Explorer, or EHE, aims to study black holes with unprecedented detail and resolution. A key focus of the Event Horizon Explorer will be studying photon rings that encircle black holes. These rings form when light orbits a black hole multiple times before reaching the observer. The Event Horizon Explorer has several ambitious scientific goals. It will test Einstein's theory of general relativity in extreme gravitational fields, measure black hole spin with unprecedented precision, probe the nature of spacetime near the event horizon, and study how matter behaves in these extreme environments. Beyond static images, astronomers are developing techniques to create the first videos of black holes. These movies would capture dynamic processes like matter accretion, plasma swirls, and jet formation in real time. These ambitious goals face significant technical challenges. The Event Horizon Explorer will require an expanded global network of radio telescopes, processing petabytes of data, developing advanced algorithms for image reconstruction, and achieving precise timing synchronization across all observation sites. The Event Horizon Explorer and black hole movies could revolutionize our understanding of fundamental physics. These advancements may reveal new insights into the nature of spacetime, quantum gravity, the information paradox, and the ultimate fate of matter inside black holes. As we peer deeper into these cosmic enigmas with advanced tools like the Event Horizon Explorer, we move closer to answering some of the most profound questions in physics. Black holes are more than just cosmic vacuum cleaners. They play a profound role in shaping our universe. Supermassive black holes appear to co-evolve with their host galaxies. They act as seeds for galaxy growth and help regulate star formation through their powerful energy output. Black holes influence their surroundings through powerful feedback mechanisms. Radiation from active black holes heats surrounding gas, preventing star formation. Mechanical feedback through jets and winds can expel gas from galaxies, directly regulating their growth. Black holes play a key role in the large-scale structure of our universe. Supermassive black holes tend to reside at the nodes of the cosmic web, where filaments of dark matter and galaxies intersect. One of the most intriguing recent discoveries suggests a potential link between black holes and dark energy, the mysterious force driving the accelerating expansion of our universe. Studies indicate that the density of dark energy may increase alongside the growth and mass of black holes. Black holes represent both an end and a beginning in cosmic evolution. They mark the final stage in the life of massive stars, but their influence extends across billions of years. By transforming stellar matter into powerful cosmic engines, they help shape the evolution of galaxies and the universe itself. As we continue to study black holes, we're discovering their profound influence on our universe. From galaxy formation to the cosmic web and potentially even dark energy, black holes are key players in the ongoing story of cosmic evolution.